Okay, back we are. Um, yeah, where did we stop yesterday? Okay, we are on the mix files actually, and what we basically want to do is to, well, read this, because this is the image data. If we are able to read this, then we will be able to, yeah, read the tile set because, yeah, we actually know its format. We will be able to read the sprites, and we will of course be able to read the sounds. So when we have encrypted this image format or frame format, we can actually start on implementing this into the OpenRA engine, which will be nice. Um, so one thing I thought a little bit about was actually the tile set file, this one. We know that a single tile has to be 64 by 64. So this should be the image. However, um, I think there were more bytes. The size didn't match exactly. Um, we'll find out because we'll now basically do the correct loader. To be able to do this, this is the position of the first frame. So it's 421 or it is 0. It depends on what the first frame offset says. So if we look at this, it says 0. So actually we need to start here and go frame after frame. There are basically two ways to do this. The first way we will later be using will be to, when we read this, we will just jump to the correct position, get the proper amount of bytes, read this frame, and we have our frame information. However, um, in this particular case, I think we could basically read everything till the file and um, no, just don't. Let's calculate this and let's read this properly. So what we actually need to do is we have our offsets here. So this is basically, let's call this image offset. And this is not num entries, but num images. Okay, so, and this is basically the images offset. Which was actually pointing somewhere. It was pointing to 421. Exactly here, 421. So yeah, for each image we just need to use this number we have stored here and add this number, and we will get the correct position where the image should be. So we'll basically move this now. We have the palette. Let's do another struct. Let's do it on top. Let's call this struct. It's an image, so let's call this image. And what we know is basically that an image starts with these information. Let's completely copy this here. So we have this in red, we have this in green, and then we have red again for this, and then this should be green again, because that's the no, this should be red again. Let's just make all the internal chunk names red. So like this, and the palette will also be green, so we can actually see where stuff starts. Basically, we don't need to read any further than here because we will read this in this loop directly. So this will just read, of course, this bytes here, but everything behind that will already be parsed, so nothing to do here. Okay, so we have this, and we need another integer to calculate. No, we don't need. But we need a return position. Let's be lazy again. We need this here, so we have an original position, and we just say, okay, where are we? Pretty important. Then we basically need to go to the correct position for the image. It has to be the images offset plus, yeah, the image offset. And now we expect an image. Finally, let's go back to the original position so we can read the next file. And let's try this out. Here we go. Image here. You see, this is a strict pattern, and then we have 40-40. Same here, same here. Because, yeah, this is a tile set, as we know. So everything is 40-40. So this is the last one. And, yeah. This is the information. What we basically know is that we have 16 bits per pixel. So we have let's use a short for that. Let's use this as colors, and we have width times height number of pixels. So let's go. Oh, and we have obviously more bytes in our structure. So wherever we go here, there are always 2 bytes unread. So let's go to the last one. If we look at this, it basically looks the same like, yeah, this, for example. So it's very likely that this is still image data, which means that the 2 bytes more are not after the image, but in front of the image, which means that we're actually reading 40-40, that this is not part of the image. Because, okay, there's a 0-2. Okay, we also have a 2 here, but it's a bit more likely because we have metadata here, like the frame width, the frame height, that this is another interesting data. Because we don't know what type it is, I can read this as short. You know what? Let's use 2 bytes, might be more precisely. So we have UNC1 and UNC2, and this might be a better idea. Let's just give binary data the blue color. So C blue, and this also doesn't have metadata, so just use C blue. So basically, yeah, we can now see this is the metadata for the image. This is the image. And basically, the last image ends here, and the next one starts here. So it reads perfectly. Now comes the interesting part. We have these 2 values, but we don't know what these values are, of course. So what we want to do is actually to not go through this list and checking 252. Yes, it's one more than this, because the first one will be number 0. We will not check everything by opening it and checking what number there is. We'll just use the log functionality and print all the values here. And let's see what it tells us. So as far as I remember, there is a print function in here. It should be printf, which has a string, a format string. So basically, we want it should be like this. Give me a number, then give me a second number, and then do a line break. The parameters are this one and this one. Okay, let's try this. Okay, there was no error, but we don't have an output. So yeah, here we go. It should be 2 and 70. Oh, yeah, my mistake. Okay, so the right value is actually positive and negative. I don't know if this makes sense. So let's use an unsigned byte. Basically, yeah, for those of you who don't know the difference between a signed and unsigned, basically a byte could be anything from this to this. So 0 to 255. However, it cannot be a negative value because there is no place for that. So the same way to basically write this in a hex way is to write it in binary. So 8 bits are a byte. This is 0. And this would be 255. However, if you have a signed value, it doesn't matter if this is a byte, a short, an integer, because it will just be more bits. The first bit here is the one basically used for telling whether it is a positive or negative value. So this, what you see here, this will be this byte value, but it will be the number -1. If we now do this, come on, yeah, it will basically say, okay, it's not negative, and we only have this range of numbers, which basically means that yeah, the number can be minus 128 to 127. This is the range for a signed byte. We have pretty different values. As I said, obviously this is not the image of the tile offset, because it has to be, or the center point, it has to be the same for all the tiles because it's tile set. I have an idea which comes in combination with the first palette ID, but let me check this. We don't have palettes. Of course, we don't have palettes. So we don't need this, actually. The interesting question is what this value is then. I actually don't know, but there's a 2 always in front, and it seems it always is. So let's assume this is a 2. This one. 2 on tiles. So we don't need this one. This can be all kind of weird values, but yeah, let's use it unsigned, because then we actually see the there we are, the values. So they might be 0, they might be higher. To be completely specific, I have no idea what this could be. Might be unused, actually. As we know, and from the sprite sheets from the units, or it's most likely units, here is a 9 instead of a 2. So it's, let me quickly check the next one. I need to run this here too, but this will crash. Okay, you know what? Let's comment this. Oh. Let's comment this out and run the same thing on this one. Actually, oh, it's always 9. Oh, and you see this number is pretty interesting. So there are a lot of sprites who actually share the same value, but there are multiple values used. But assume the first one, this is always the same. It's 2 on all the tiles. It's 9 on all the sprites. I guess all? Yeah, all. So it's very likely this is some kind of, let's call this compression type, or yeah, let's call it just type. So we know 2 means it's a tile. 9 means it's a sprite. And maybe we will find some other values. So for now, if the type is 2, so if type is 2, then we basically know that it's just 16 bits per pixel, this stuff. Else if the type is 9, then basically to implement me. And else, you know what, we will just yeah, we will just print this. So we'll just do some kind of unknown type and give him the type. So if this ever happens, we will see it in the log. Let's see, output, Windows output. I should not close that. Let's run this. Oh yeah, it's no longer unc. So remove this one here. Maybe completely comment this out. So actually, yeah, we don't have anything else, or we don't have anything else yet. It might be very likely that there is sprites are sprites, okay, but it's likely there is a difference between a sprite who might obviously have some some information like yeah, an offset on the x and the y axis, and it has some compression. It might be possible that there are other kind of file types or image types in these containers for the UI, because they obviously, yeah, they most likely don't need a center pixel. So all the offset stuff, whatever might be a good idea to have in sprites, yeah, might be missing here. So it is possible they made a different number too. Also, if we actually look at the format, we have number 2 and we have number 9. These are very strange values. So I don't know what if the type is 0, 1, or 3 to 8, or something above 9. Might never happen. It might actually be in one of the other mix files. So yeah, for now, let's just leave it as it is. We can actually read this one. It was, yeah, pretty simple to do. This one kind of was not used, or not useful. We don't find a use case. But now let's see into this one. Let me close this again. Okay. I'm stupid. I need to open it again. So let's put this here, because we actually, what we now want to do is to read file type 9, because file type 2, as we know, yeah, we are completely through the file. No more to do here. We are done with this one. I've asked today on the OpenRA IRC if it is actually possible to load 32-bit palettes, not palettes, tile sets. So a tile set which is not using a palette. Not yet, but it shouldn't be much work. So I think before I will do the video where I load up the tile set and implement it, I will work on another pull request I'm going to make, which allows tile sets to use 32 bits per pixel for the tile sets only. I don't think we actually need this for the sprites, because yeah, anything in game which contains stuff like units or whatever, they have player colors, and there are just 2 types to get player colors, or 2 ways. The first way is actually to have the same unit twice or 3 times or 8 times, depends on the number of colors you can choose from, and everyone has a different color. But as we know, this is using a palette. It's very unlikely. It's more likely that some specific colors in the palette are being swapped. Yeah, so we'll check that. Okay, so let's do file type number 9. Actually, here's where we are. We have a 9 and we have this number. Let's see if this makes sense here. We have a... Oh wait, we'll just lock this again. Run. Okay, so the values are, the largest value is 74, and the smallest value is 45. Wait, 45, I've seen that again. Actually, here, this one. This one is 45, and it seems to be the first number used. So if we add this on top of each other, so it will be by 80. And we know there actually were some. Let me see quickly. There were some empty palettes in here. Here we are. They are all 0. So it's likely that this was what I expected them to be. Yes. Okay. So it's very likely that this is definitely the first palette ID, and this is actually the palette ID this frame is using. So we can let's assume this is correct. So let's call this a palette ID, which basically means that whatever is in here is not used for file type 2. It's basically an ignored byte. Wherever it is in here, I don't know. It might actually be possible that all the colors a specific tile is using can also be found in this palette ID, so that internally a tile set is really using just 256 colors. We definitely need to check that. If this works out, we can of course get around the need to implement 32-bit per pixel tile sets into OpenRA. but this means we basically need to undo the palette or reapply the palette. So we need to go through all the tiles, all the pixels, find the correct index in the correct palette, and yeah, assign it. I don't think this would be a good idea. So anyway, so this is the palette ID, and yeah, we have 35, so this will be added on top, or in other words, it will be subtracted. So if this is the palette ID, we need the palette start at first. So let's call this first palette ID. We will basically, yeah, use this name, put this here, and where's the image here? We'll basically tell every image the first palette ID. So we have this number here, which is basically, yeah, the large one, and we need to subtract this number to get the correct one we can use from this array. Or it will be an array, of course. Currently we are just reading single values. Okay, entry here, no, image 0. So let's try to read this image. What we can actually see is that we have a very clear pattern here. It starts with 0, 2, 4, 6, 8, A, C, and it repeats all the way to actually to here, and then 70 is repeated a lot of times. So this is basically a fixed structure containing a lot of shorts. Maybe this too. But it's a 0 value here, another 0 value. So maybe it actually goes to here, or I don't know, or maybe even further. What we however know is that this beginning part here looks different. It looks totally different. So it's very likely that format 9 has even more data here. So for now, let's how many values are there? Let's assume it's actually something like this. Yeah, why not? So we have 4, 8, 9 values. Let's just do this very quick. We have 9 values, so let's just call them Ang1 to Ang9. Here we go. There they are. Oh, they shouldn't be blue. This one has to be blue. Okay. So this is kind of interesting. We have some values. They are not, yeah, they are pretty random actually. But what we do know is that the image has 80 by 69 in the size. This has basically the same, yeah, the same size. Let's check this on the second one because it might be possible. Something which has a different size. 5938, 5938. So basically, let's call this with copy and hate copy. It's likely that oh, this one is a short. Very important. So there is a maximum size. The int might be larger. However, I'm pretty sure that the number here won't ever be larger than the short because it would be a huge image. Yeah, let's call this hate copy. So basically, this is another hate and width. What else do we know? Let's get back to the first one. Run this once again. Okay. This is a larger value. I'm actually thinking that this is yeah, it has to be a pointer or a length because it's pretty big. So let's just assume it's a point. Let's call this offset length amount, something out of that. Then next one is 70. It's a small number. Let's just note that we know we are talking about 70 for this first frame here. Then we have 127. Okay, why not? Then we actually have 36. Then we have 176. Then we have 316. And at last we have 443. Which is, they are also kind of large, but they're actually getting larger, which is interesting. So what do we know? Let's just see where we are. We are here. The image actually started here, and we are here. So the header now has a size of 42. Nothing special here, but actually this was this was the upper header here. This is basically the second header. It has a length of 36. This matches actually. So let's call this, maybe second header size, maybe. We don't know. If this is a header, it has to have always the same size. So let's check something else here. We have 108 as the third value. Okay, then we have 26, then we have 45, then we have 36 again, which is very unlikely because these are totally different frames. And then we have these numbers. They are also getting bigger. So as the header is quite small, this might be an offset because it's getting bigger. Yeah, let's assume this is the header size because it actually it fits. It could be possible that some offsets for the rows are actually without the or including the header size, and someone actually saved them here to subtract them or add them. Let's not speculate about that. Maybe we need it, maybe we don't. Okay, so let's get back to frame number 1. Actually, what we have here afterwards is basically there is a 0, 2, 4. There is some stuff in here. What could this eventually be? I don't know. Could be the row offset. How many numbers do we have? Let's just select. Let's assume this much because 7E. Yeah, it could be more. I'm not sure. But what I am pretty sure is that this is something else, basically, if you look at these numbers. And this is some image data. So whatever is in here, yeah, let's just try to find a pattern. So we have a 0 on the second number till here. But if we make E8 larger, we will get 117. So 2. This is also still getting larger. Basically, till here. And the next block here has a different pattern. So okay, this is 280. Not very interesting. Are we sure about the last 0 and the first 0? Which I don't know. Maybe we should look about what else we have here. Okay, if the image is actually starting 1, 2, 3 here, we have 36, which was this size. Let's get to 70. Nope, that's definitely not what we're looking for. Let's try 70 from here on. 70 shorts, so 140 bytes. Should be this much. You see, actually, there's a 0 here, and afterwards the values are different. So yeah, it's quite likely that this 70 is a number of entries, and these are the entries, because yeah, basically this breaks the pattern. So okay, so we don't know what it is, so let's call this num_unc4. This is a number. So okay, we need our loop value. Let's make this stuff. Yeah, just use another variable. Oops. Let's give it another variable, and let's loop over this. So basically, what we want to do is this. We want to read a short. Let's call this unc4a, because it's the first thing in the unc4 block, and we are not using I. Okay. So this actually looks quite nicely. We don't know what it is, but it's actually, yeah, as you can see here, 002468. How many lines are there? This is an interesting question. 70. The more interesting thing is actually that we have a height of 69. So this could be one entry per line, but we have one more entry. So maybe the first one has to be skipped because we have 2 times the 0. Let's check the last ones. We also have multiple times the last one. I'm actually not sure about this. We have 17 and we have a height of 69. So it might be possible that one line is not used at all. Or it might be possible that something is duplicated. Whatever, I don't know. We will speculate this later. So as we actually know, this is a number of unc4s, and then we have a different pattern again. And yeah, maybe it's always 0 in the first one, because this is for the row number 0, and the image is actually using number 1, and so on. Anyway, let's try to get this done. It's very likely if this is the first one. Let's just try if this also works for this chunk. Let's call this num_unc5, and do the same for unc5, and just read unc5a. We don't need an a because actually it's just one value. Let's give it a go. And actually, we read this stuff till here, and I'm pretty sure that this is also part of this chunk, because you know this 9-3f is repeated a lot of times and ends with 3e, so it's possible that 2 bytes here are also part of this. Let me think. Yep, this is interesting. What I thought. These are 2 blocks. It's not 1. So okay, assume there's no unc10 here because we have a 0 again here. Let's try to read this 2 times. Let's call this okay, unc4a and unc4b, because maybe there are 2 values for this one or this one, or maybe we had to read this. Let's try it. Would be a luck shot if it works, but who knows. Okay, so the unc4a basically starts with 2 zeros, then 2, 4, 6, 8. The unc4b is also starting with 2 zeros, 4, 10, 16. Okay, and the unc5 is it's not starting with a 0, but it's starting here. This could work. Let's see the values. It's getting bigger and bigger, and oh, there it breaks. But I'm pretty sure I see a pattern in here, so this could also be an UNC4. Well, because why not? Nope, it still breaks. So let's check if this is a smaller value. Let's check for an unsigned byte. Nope, the pattern definitely goes over here. But this one was bigger. Let's try it again with this one. Oh, this looks good. This looks very good actually. And yep, 3A, 3A, 36, and a 0. So we have a 0 at the end. Okay, this seems to work out. So let's assume this is basically good what we are doing, and we're not doing some weird shit. Okay, then we have these values. They are getting bigger, so what I'll assume now is that if I basically start with a with copy here, so let's just check what happens if we want to check how many bytes are we actually reading. We are actually reading 443 bytes. Oh, 443. Nice. So basically, we can tell that UNC9 is pointing here. And if this one is basically pointing there, I'm pretty sure that UNC8 is actually pointing here, that UNC7 is pointing here, and as we know that this is the header size, and this whole thing is the header, then I'm pretty sure that UNC6 is actually pointing here. So let's call this header size. Well, you know what? I think this is the number of UNC4s, and this here is basically the UNC4 offset. Yeah, we will name this later, but I'm pretty sure this works out. So let's try this. We have the UNC4B here. It's basically starting here, so the number of bytes are this. It are 177. Oh, wrong selection. This 176. So yes, this fits to this amount here. So 2 of them are confirmed. And let's check this one. It starts here. So basically here it's 316. Yep, it's confirmed. These are the particular offsets. So as we don't know what this is, let's rename this stuff, because I think this might be a good idea to do so. Otherwise it will be a little bit weird with all these weird names. So let's call this number UNC1, number UNC2, and oh wait, yep, this is number UNC1. So this is the first UNC thing, this is the second UNC thing. Then we have the UNC2. And basically we have here is the, no, here, this is the UNC1 offset, 1A offset. Yeah. Then we have the UNC1B offset, because yeah, it basically points here. Then we have the UNC2 offset, and it points to our UNC2s. And then we actually have a last offset. So let's do some separators here. Number of UNC1s, number of UNC2s, then we have the offsets, and actually this is not related to the above two things, so I'm pretty sure. Let's see what was behind all this weird stuff here. This is a totally mass data block. So this, I think these are the pixels. So let's call this data offset. Okay. I will remove the spaces when I know what UNC1 and UNC2 actually is. Okay, so we still have this weird number here. Let's see if we can find a proper usage for that. Okay, where it is. There, it's a 3,475. Pretty large. Might be the whole file. Okay, let's see where the file ends and the next file starts. There it is. We have 3,918. It's wait. If we basically use the 3,918, 18. This is the size till of the whole file. And we basically subtract the UNC9, which is 443. We actually have 3,475, which is this number. Haha. So, okay, there's a weird thing actually. The data size is here. So it's very likely that data size is the size of the compressed pixels. This is where the compressed pixels start, wherever they put this here and not on top of here. But okay, that's how the format works. Let's call this to-do pixel format. And yeah, we have to decode the pixels now. Okay, so we have the basically have all the metadata, and we can now go over to extract the pixel format. Yeah, the first. Oh, we have actually numbers here. They are 0 to, let's see, 126. So this is kind of interesting because let's 0 to 126. They are always +2. So whatever they are basically getting larger by 2. But if you look at these blocks, actually, they have a length of 2. So it might be possible that this is pointing at this. And because we know that these are actually also 69 entries, 70 entries, sorry. With the first two are unused, they are 0. So we are back at 68 entries. It's very likely that this number actually points us to one of these blocks, as I said before. So the compression may likely be something like go over this this particular this values, and then take the value what we are reading here and go to the proper number, or to the proper offset in the second one here to get the second number. So this one just maps this, and these numbers are pretty larger. So and they are also the same here, and the top ones I think were they're also the same. Anyway, so the top ones are basically pointing to this. I'm not sure if we need the top one then. And these numbers are most likely they are not equal. So they are, if they are pointers, they are not pointing towards one of the integer values. So the biggest one is 3,475. And actually, the interesting thing is, I think I have read this number, 3,475. This is the number. This is the size of the data. So they are basically pointing to the file end, the last ones here. These are all pointing to the file end. So I think it's possible that this is basically the offset inside the yeah, this block with pixels. So we have an offset where to start. The question is, how long is an entry? Yeah, that's stuff we actually need to find out. Okay, so we actually now know that we have some values here. We have some numbers. We have some offsets. Yeah, pretty interesting. However, what we actually need is a way to read the pixels, which are here. So let's do some debugging. No, it's not log. It's printf. So we're actually printing a specific number. What we actually want to print is the number of data we have, because we need to know if our logic actually fits and we actually read the correct amount of data. So let's do this. Basically, it gives us a lot of stuff. We now need to find a logic which basically returns the same number. So let's oh, there's an old load left over, but let's use a temporary variable. And while we're actually reading this, we will basically do something like temp++. Not plus plus. We will actually add whatever we read here to the temp to make it a little bit more, to give you an idea what I'm talking about. The first value here we actually want to do is read bytes, and then we have skip bytes. Basically, read bytes means read this bytes from the image, and skip bytes means now just skip or skip pixels, skip this amount of pixels. Okay, you know what? Let's call this pixels so we don't mess this up. Which are basically not red; they are basically transparent in the target file. So if you have a unit and there's transparency around, there's no need basically to, write all the transparency bytes in this format. So, okay. Also, we have a mode. Basically, we are always reading, writing, or in this case, reading, skipping, reading, skipping. So we need a bool. Let's call it local boolean. Or is it called bool here? I don't think it has a bool. Let's just use a byte then. I don't know, or an int. I don't care. Let's call this mode. Let's before we start, let's first do the mode is 0. The read pixels are 0. And of course the skip pixels are 0. So now assume that we just need to read through this list, which is this, and it tells us, read 36, skip 4, read 35, skip 6, read 35, skip 6, and so on. So what we are going to do now is basically we read this value, which is one of this bytes, and we basically say, okay, if mode is 0, so we are in the read mode, then we are going to do something like read pixels plus whatever is here. Let's call this num pixels. I think that's a better name. So you know what? Let's call this num pixels list. Entries. Entries might be better. Let's call this num pixels list offset. So we have a list of this pixel amount, and we're basically doing this. And I just noticed I'm stupid. We don't need mode actually, because we can just check this value. Basically, if if this is modulo to 0, which basically means that it will match on 0, on 2, on 4, and not on 1, and 3, and 5, and so on. So in this case, let's assume we have this case and this case. So if this doesn't work out, we assume we are basically going to skip this number of pixels. Now for debugging purpose, let's just add this and this, and also this. So now we want to know read pixels, skip pixels, and what we also want to know is width times height, because this has to be the correct. And let's once add this. So plus. Okay. So this should be everything which we are interested in. Let's use the full available space because the line is getting a little bit longer. Let's click run. And it's done. The output. So what we can see here is the first image. It should have this length. And actually we are having this length. So yeah, we are missing pixels. But this is interesting. The first numbers are matching. So this one and this one also matches. So which is basically the data size and the skip pixels are matching. That's quite interesting, which basically means that we just, yeah, it's the opposite. So we are basically starting in the skip mode, and then we get a read mode. And if we now do this, okay. So the first two numbers are always equal. So the number of bytes we have been reading, and the number of bytes we have in our file are equal. So we're reading all the bytes. The file, the number is not bigger or smaller, so it's perfectly. The only problem is actually we're skipping this much. We are basically adding these two. We're getting this number, not this number. Why does this happen? Very easy, because it's likely that this pair of information is basically skip this much pixels in front of the image. So of this row. So if we're reading a particular image row, we want to skip this much empty pixels because yeah, they're empty. But then we're just not going to continue on this. This is the next row. So basically we are reading the image row by row. This is very important to know because actually this means that what we're actually doing is let's assume we want to have an image which means empty, empty, pixel, pixel, empty, empty. We are currently using the skip. We are doing the read. And we are actually assuming that the next byte tells us how much we have to skip and to read and so on. But basically, what we need to do now is fill up the line or the whole row with as much as needed empty pixels, because the next byte is basically the next row. So yeah, pretty easy. We're going to the number of entries here, which we now can divide by 2, because we know there is a particular pattern here. Basically, we need the skip pixels, we need the read pixels, then we god damn it, I can't give it the same name. You know what, let's call this underscore, I don't care, because they're for debugging purpose only. So we're using this one, we don't need this, and we don't need this, we don't need this. So let's get back here, So let's count all the read and skip information. Skip pixels, read pixels, so we should still have the same out. No, why? I still have somewhere the old. Yeah. Stupid me. Okay, again, the first numbers are matching. The second, this is the skipped amount. Oh, and yeah, this is wrong.
But still, we don't have enough, but we need to fill up this line. So basically what we need to do is, we need to skip even more pixels. Basically what we want to do is, we need to add the number of pixels we need to fill the line. We know this because this is the width of the image. And basically from this width we are subtracting the number of pixels we already skipped, and then we subtract the number of bytes pixels we have written. So this should be the left pixels should be, yeah, or the amount we get here are the pixels we need to fill, yeah, to fill this line. If we now press play, it still doesn't fit. Interesting. Let me think. We have the proper amount of, we have everything red. Oh yeah, one thing we didn't count in yet is actually what would happen if we have this tables here. If a particular line comes twice, this is a second type of compression. So imagine we have an image and we have blue, 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 red, red, red. And then we have another line like blue, blue, red, red, blue, blue. And then we have the second line again. Then a good compression would basically say, hey, this is the same line. I don't need to write this line twice. I just need to say use this line and then again use this line. So basically this means that all this logic here has to be wrapped actually. This is correct, of course, but this is what's interesting. This value here, the unc1, basically tells us which line we want to read. Because let's go up. The value starts with 0 and it gets bigger. So this is basically, it's not unc1, it basically tells us how should we call it? Let's call this scan lines, because actually, yeah, these are the lines. So then we have a line offset. The line offset basically tells us which line we want to read. Then we get into the second block. Wait, this is scan lines offset. So this tells us, okay, now use the first line, the second, and now again use the second, and now use the seventh line, and whatever. This is for the line compression. And it basically points us to here. So what we want to do now is think about what could be in here. Yeah, well, it's pretty easy. This just tells us which of these blocks we are going to use, and this block basically tells us where we should jump to read this. So this is basically, because we know that this is perfectly +2 stuff. Yeah, of course, because it's the next and the next and the next short. The second block here has different values. Basically because this is the proper offset where to read our stuff from. Wait, let me think. This should actually be the offset here in the pixel data. So it's likely possible that we do not need this for the compression at all. Yeah, it's very likely possible. So basically we just need to read the number here. Now we go here to the right line and do the same we already did. Okay, so let's try this out. Okay, let's go. We need to set this to 0 because it has to be initialized. The first thing is we need to do now is basically we need to scan lines, and then we basically get the what we get here is the line offset, of course, yes. Okay, so basically we have the scanline list. We are basically reading through all the scan lines, and we're getting a number here. So what's pretty important is that after we have read this, we will return. So for now, I will just to return to this position, I will just copy this over, basically. Come on. So we're reading this line offset. Then we actually we need to store where we were. So let's use the scan lines offset is telling me the current position. I need to define that so it doesn't crash. local and scanlines offset. Okay, after I now know the position, I now need to go to the target position. So we basically need to start at the image position, because all offsets here are from this internal image or frame position. Additionally, we want to go to the to exactly this list here, which is the third one, which is how did we call that? Wait, this was the we had the data size. Okay, then we had the scan lines. Then we had let's call this just Ank1 because we don't need this one anymore. Then we have the scan lines offset, of course. Yeah, this is basically where this reads. Then we have the Ank1 offset because that's the part we actually I think can skip safely for now. We don't need it. And then we have our num pixels stuff. So we have the num pixel list offset. Wait, where do we have the number of entries? Oh yeah, it's actually the, let me think, num pixel list offset. We had this number telling, okay, forget it. This was the scan lines, and this is actually the num pixel entry list. It's the old one. Okay, so we don't need this one, we don't need this one, but we need this one. So basically the let's call this a pattern offset because that's a pattern. Yeah, skip that much, read that much, done. This is a read pattern. So what we now want to do is basically we want to go to the image position. We add the pattern offset, so we're actually going to the to this list of patterns. And now basically let's let us use the correct. Oh no, let's call this pattern offset because this is yeah, as you could guess. This is the correct offset of the pattern. Pattern offsets plural because this contains all. This is the offset to all the. No, come on. I need to redo this part. This is the offset to all patterns, so plural, and this is the offset to this specific pattern. So we go to the start of all and then hop to the correct one. And now we're at this position, we can basically do exactly this. We are now at the correct position. We now know, okay, we need to skip this much pixels and we need to read this much pixels. So this is a line information. We can also do the same here. And all we need to do now is to read the correct pixels. We will do this later because actually when we now are doing this, this should match. Okay, what does he say? User scripts to add this one. What? Scan lines offset? Oh, because, yeah, I have the same name. Let's call this temp position. I don't care. So, there we are. Then we jump here, then we read this, and then we go back to this position. Okay. As we can see, we are reading too much bytes. This is kind of interesting. The question is, why are we reading too much bytes? Actually printing how much do we read? This is the number of bytes in our file. We are reading more bytes. Why is this? Because we are reading some lines multiple times. So yeah, this is quite correct that this number is bigger. Then we're actually skipping a lot of pixels. And then we actually, yeah, this is how much bytes we were reading. And this is the total amount of pixels we should have. So the question is there a particular amount? Okay, 80 here. Let's look further. This is interesting. We should have 1, we have 2. This is a weird one. So this is a 1 by 1 pixel. It's a single, yeah, a single pixel actually, and we have a 2 here. So what we're actually doing is we have read 1 pixel twice, or 2 pixels. I think 1 pixel twice, and we didn't skip any pixel, and then we were done. So let's assume we're having 1 row too much, because yeah, let's assume this could be. So if we set this to 1, oh, ta-da! This fit nicely. Why did I do that? Because actually, if we look back, then we always had this at the beginning. Number 0 and number 1 were always both 0. This is a very weird thing, actually. So I just assume that the wait, you know what? What I'm thinking actually is that the don't ask me what I'm thinking. It might be wrong. Okay, so yeah, this is the first list we are reading. We are currently skipping the second list. And we are basically then, yeah, we are reading this from the first list, here this value. Then we are basically, which tells us which line we want to read. Then we are just hopping over into this table, or this list, where we are reading the pattern. And then basically we are, all we need to do now is basically to hop into here and start reading the number of bytes. However, this is a pattern, of course. It doesn't say us where this pattern starts. So this is where this list comes in. So let's add this, and we are complete. Anyway, okay, so every entry here must have an entry here, because this is telling us basically where this line starts. So this is basically telling us use this line. This is telling us where this line starts, and this is telling us the pattern of this line. So the interesting thing I'm actually thinking about, yeah, we are actually leaving out this one because we made this 1. So we should do this and basically reread this, and for now we can do this later code-wise by just you know what? Let's read 1 less and just do something like just skip 2 bytes. So we are basically skipping this 0 here, and assume this is the first one. We are reading at 0, and this 0, I don't know why it is there, but we are just skipping it. Okay, so here we go. This is the same actually, because we have, well, it's interesting. So maybe there actually is 1 more row than the image is in size, or maybe even the height here is wrong, but maybe the image is 1 more in height than and tells us, because it says, okay, it should be 69 rows, but we have 70. This is actually pretty obviously 1 more. Okay, you know what? We can, I'll do something else. I will basically just assume we have 1 more row than we should have. So we can remove this, and we're basically reading this, and the numbers should fit again. Let's see. Yep, numbers fitting. Nice. So okay, to get hand of our bytes, which we actually have to read for the second value every time here, need to hop into here and read the correct offset. So in addition to this, we first, we need the temp position, because we have to return here. This belongs to here, and we need this in between. Basically, what we want to do is we need to go to the data offsets. It's basically all the offsets for all the data. Actually, this is a data offset, because it's an offset which points to the data offsets. So we are going from here to here. We actually, adding the pattern offset, we actually had a red here. So okay, read this number. We go into here, and now we are going to read the actual data offset, basically the offset in the lower block where this particular row starts. Then we hop into this third table, which we already had. We're reading these two things. So now this whole thing in the middle should be green. Nice and not so nice, because this is a short. And again, this is way better. It's actually interesting that there is some data in between. It's actually pretty interesting. I don't know how this could happen, but this, if I look at this data, we have 93D, 93D, it's all the same value and it ends with 0. So I'm actually thinking that this is some filling up stuff. 93D is actually, if you look it to the right, it's 3,475, which is the data size. So yeah, this is basically pointing to the end of the image, so there is no data here. So yeah, it's actually filled up. This is trash data. We don't need to read, because yeah, there can't be any byte here because this is the end of the image. Okay, we now have the correct offset. We have this, and the last thing I actually need to do now is we need our correct pixels. So after we do all this stuff, basically we just need to do one more thing. Oh yeah, this is just for calculations, so just put this here. What we basically need to do is we need to go to the data offset. Wait, I'm an idiot. Let's not call this data offset, but we call this pattern data offset, because this is data offset for this particular pattern, or not for line. I don't know. Bad idea, bad idea, bad idea. Let's call this not data offset here, but let's call this compressed image data. So we're going to the image position from the top. We are actually going to the compressed image data, and then we are adding this one. So now we know, now we are at the correct position where our pixels are, and we actually know that this is the amount of pixels we have to read. So what we now need to do is just one thing. We just do this, which will actually crash because, come on, it will tell us you can't use a array inside of a loop. So yeah, just for this case, I will do a temporary struct. That's the limitation of this application, which I think there was a workaround, but I can't remember. We will clean this up when we are going to do the sprite loaders. So for now, let's call this pixels. I don't know. So, and actually, we need to give pixels an amount, and all we do is basically now tell him to read this amount of pixels. So something like this amount of pixels. So instead of this, we just say, okay, this is pixels chunk struct, and this much pixels. So oh yeah, and this one has to be blue, of course. So this goes here. Okay, and go. And as we could see, we are reading over the end of the file. This is something we have to fix. But actually, this looks pretty good, actually. So yeah, let's check it out. So this is the first line. It tells us go to 0. Then we go here. It tells us also, okay, go to 0. Then we go here. It tells us, okay, just read 36 pixels and skip 36 pixels in front, and then read just 4 pixels. So now we go here, where this thing starts, and we'll just read this 4 pixels. The next one is the same. It's the same 4 pixels we are going to read, and then it tells us, okay, read 6 pixels, so we're going to here and wait. Data offset is also 0. Is that right? Well, it could be. Eventually, let me think. I think what are we actually doing? We are using this pattern offset. Oh, maybe we do not need to apply this on the first list, but because we just need, maybe we just need this value, and then from the second list we need this value, and then we hop into this one and read this thing. So maybe this is just nothing more than we need to hop from here to here. So basically, what we need to do is we need to hop over by a particular amount of scan lines times 2. This looks almost... the number is okay, but still we're reading over the end of the file. Okay, why is the third value negative? What is this third value? It's the skip pixels. This shouldn't be negative at all. Yeah. Anyway, this is something we can actually later debug in C#. We can actually see have some output visible, and we can actually see where we're actually not reading this stuff right. So for now, let's assume we are correct. We have these scan lines here, which are basically telling us the amount of scan lines. Then this is basically the you know what? Let's call this num scan lines, because yeah, I like this to have a particular pattern. Then the next thing actually was the num patterns. No, it was divided by 2. So then we have the offsets to the scan lines. Then we have the offset to the data offsets, and then we have the offset to the patterns, and then we have the offset to the oh no, this is the data size. Compressed image data offsets. So then we have the offset to the pixels. So now we actually are reading from the first table. Then we will store this position because we have to return there. Then we hop over to the next table. There we get the offset where our pixels begin. Then we basically hop over to the third list where we basically hold this 2 information. So okay, they could simply have put all these 4 values after another, but okay. So from there to there to there to there. As these are offsets, I think it might be better to use shorts here just to be safe. Let's run this. Okay, scan lines. It's num scan lines. Okay. Yeah. So we are reading from this. Then we're reading from the second list this value. Then we are hopping over to the third list, where we are actually reading the pattern, and then we are hopping into the image data and the correct position, and then we're actually reading the for this pattern. So we are assuming we are skipping this much pixels, then we are assuming we are reading this much pixels, and then we are skipping everything to the end of the line, and then we go back. So this works quite well. So actually we have a crash here because somehow this actually fails, as we can see. This is a weird thing that there is a single color in here. Okay, this is even weirder. Yeah, as I said, we can debug this later. So for this video, we are almost done, or we are done. On the next video, I will try to start on adding the converting this actually to make a file system loader for OpenRA, which is able to read WD files. Secondly, I will start on doing a mix container reader. When thinking about it, actually we need to. Yeah, we have a package in a package, so a little bit weird. Anyway, so yeah, the next on the next video I will basically have the goal to get visible sprites in the game, which which is nice to see. I will skip the sounds for now. I will skip the tiles head. This will be also later videos. But the goal is clear: get this stuff to read, and everything else in the next video. So see you there.